Okay, we're going to go through the second part of this paper, January 2021, Physics International A-Level for Edexcel, Unit 2, Waves and Electricity. We went through the multiple choice questions and went through questions 11 to 15 of section B. So if you watched the previous video, I left you with the answer to question 16 on the screen. So some of you may have already seen this answer, but we're going to go through it again. I'll just zoom in one more bit. Okay, so this, as I explained at the end of last video, it's two graphs showing the characteristics, the voltage current characteristics, for a thermistor and for a filament bulb. Okay, so this is a negative temperature coefficient thermistor, and for those of you who aren't sure what that means, it means that the resistance varies inversely with temperature. So if temperature goes up, it actually releases electrons, because it must be some kind of material like a semiconductor where you increase the number of conduction electrons, and that's what the question's about. They want you to explain the two shapes of the graphs. They say explain the shape of each graph. Your answer should include reference to the movement of conduction electrons in each component. So basically, overall, the temperature affects a filament bulb by increasing the resistance due to the lattice structure vibrations, and a thermistor, the increase in temperature for a negative temperature coefficient thermistor. As it gets hotter, so that you put more voltage and therefore more current in it, it will get hotter. This actually releases some electrons in the material and promotes them to the conduction band. They're usually they will not be delocalized. So it's probably because the thermistor is made of a semiconductor type material. So how do you get your answers in such a format, communication-wise, to be able to get the 6 marks? So the 6-mark questions are always indicated by this asterisk at the beginning of the question. So it's the quality of your written communication. So these are why I do these videos, is to show you that clarity of communication, both writing and in mathematical communication, is what gets you the marks. So you need to practice these. You need to practice questions as much as possible, even if English is your second language. I have students who speak very little English but are doing advanced level physics, and they go through every single A-level question they can find from the papers and do every paper twice. So for the filament bulb, you could say as the voltage increases, so they've already defined V as voltage, so I think they'll give you the mark without writing the word out in full. Normally it's safer to write the word out in full. As voltage increases, so does current, but not in direct proportion, as the resistance increases with voltage. So that means, why does that happen? So if the current doesn't increase in direct proportion to the voltage, it's struggling to keep up with so when the voltage doubles, the current doesn't double. Okay? The increased resistance is due to the temperature increase in the filament. Okay? So you put energy in. Remember, voltage is joules per coulomb, so you're giving more energy to the charges, and that these collisions will gradually increase the temperature of the material. Okay, so this increases the vibrations of the metal's lattice structure. Okay, the lattice structure is the way we explain the metallic bonding. All the atoms are in a lattice structure, a rigid structure. They're made of, you could say they're made of ions or atoms. They would be ions because some of the atoms have lost their electrons and they become conduction electrons. Okay. Anyway, as long as you've explained that concept, there's your 2nd mark. The 3rd mark, these vibrations result in an increased rate of collisions between the conduction electrons, which is what they wanted you to mention, the conduction electrons, that means the free electrons or the delocalized electrons, and the ions or atoms in the lattice structure. This makes it possible for the current to increase, makes it impossible for the current to increase in step with the voltage. So that's the answer that you need to put to explain the shape of the graph. So in that case, the gradient is decreasing. A decreased gradient with the voltage on the x-axis would mean that resistance has increased. Okay, but they're not after that. They want you to explain it in terms of what's happening to the conduction electrons. So again, 3 points for the filament bulb, 1, 2, 3, and that this quality of communication, I don't think that they could find too much wrong with it. For the thermistor, so I've underlined filament bulb, underlined thermistor. See, now I'm looking at the thermistor graph. In this one, as the voltage increases, the resistance decreases, because this time the gradient, is going the other way. So this time the gradient is getting steeper, and with voltage on the x-axis, the steeper means the resistance is decreasing. So here resistance has decreased compared to the beginning, and here resistance has increased. As you go to higher voltages. So going back to the second part of the answer. So as the voltage increases, the resistance decreases, unlike the filament lamp, or opposite to the filament lamp. This is because the number of conduction electrons increases. So this is important that you know that this happens in a negative temperature coefficient graph. That's the second tick, because it's released by thermal energy. Okay, so in effect, N goes up in the equation I equals NAVE. Okay, we're assuming everything else remains more or less the same. E is a constant. In this case, N is not a constant because it's a negative temperature coefficient material. This leads to a higher current, as I is proportional to N. Okay, so assuming nothing else changes, if N goes up, I must go up, which it is due to the increased number of conduction electrons. So that's question 6, the 6 marker. Okay. All right, so question 17 is about the photoelectric effect. Just showing you, I've done a bit of calculation at the top of the page as well. So question 17 is talking about ultraviolet light, and it gives you a wavelength of 20.0 nanometers. So first thing to note is nano is 10 to the minus 9. So once you know the wavelength, you can also work out the frequency, because the frequency comes up in the photoelectric equation. So if you want to work out the frequency would be this much. You could alternatively change the equation for the photoelectric effect, which is this, commonly written as HF equals phi. Phi is the work function. It's the minimum energy required to release an electron. In other words, the electrons which are closest to the surface require this much energy. They've noticed this is given to you in electron volts. Electrons are released by the photoelectric effect. Calculate the minimum speed of the electrons. Well, in this equation, this is the energy of the incoming photon. This is the minimum work that you need to do to get the electron to the surface. So 3.68 electron volts. And then the rest of the energy that the photon gives can be given to kinetic energy of the electrons which are released. Okay, so electrons are released and they gain kinetic energy. The maximum energy they'll get is if they're close to the surface. That means you didn't need to do more than the work function to get them to the surface. Okay, so this V max comes from this equation. So that's the starting equation. So at first I thought I'd put HC over lambda to do that, but the mark scheme gives you a mark for working out the frequency. So if you work out the frequency using the wave equation with the speed of light divided by the 20 nanometers, you get 1 mark for working out the frequency. So I've gone back, I've changed the subject of the equation to put the subject of the equation to show that Vmax comes from there. So it's HF or HC over lambda as I've written it. So you can put it back as HF because I've put the frequency in, minus the work function, which is 3.68 electron volts. Okay, well, the HF would be, that's H, that's the frequency we calculated above, that's the first part of the equation, and you need to change the work function from electron volts by multiplying it by the electron charge to get it into joules. You need them both to be in the same units. And if you don't know how to do that, this comes from the equation E in joules is equal to the charge, which is the electron charge, multiplied by the voltage, in this case 3.68. So 3.68 volts will accelerate an electron to gain that much energy. Okay, so this is the energy equation that is commonly used in A-level. So once we've worked out this is 9.95 times 10 to the minus 18, yeah, you'll probably get a mark for working this out. And you'll get a mark for doing this one, no doubt. 5.89 times 10 to the minus 19 is working out the work function in joules. So then the difference in those two is how much kinetic energy is gained. So that's the answer there. V squared is therefore equal to this divided by the mass, multiplied by 2 because a half goes on the other side, and then you square root it and you'll come to 4.53 times 10 to the 6 meters per second. I hope that's clear. Remember, you can stop the video at any stage and copy down the answers, which is what you should be doing. Okay? Alright, so this is the second part of the question, part B, then goes on to student suggests that if the wavelength and the intensity of light are both increased, the maximum speed of the electrons released from the metal surface also increases. Well, if you increase the wavelength, what are you doing? Well, if you increase the wavelength, you're actually decreasing the frequency, which therefore decreases the energy, because energy is proportional to frequency. So increasing the wavelength would have the opposite effect to what the student suggests. This would lead to a reduction in the maximum speed of the electrons released. In fact, it could stop. If you increase the wavelength, you decrease the frequency, it could have insufficient energy to even be equal to the work function, so it may not release any electrons. So it would reduce anyway the maximum speed and possibly to 0. So then increase the set. So there's 2 marks for understanding why the wavelength should not be increased, but increasing the intensity could lead to more electrons being released, as more photons equals more electrons, potentially. But if you've also reduced, the reason I've said could, yeah, you could say should. That's as long as we haven't reduced the frequency by increasing the wavelength to that level where it doesn't meet the minimum requirements. Okay, so that's why I put could. So should would be probably a better way of putting it. Should lead to more electrons being released, as more photons equals more electrons potentially. Why is that? Because, however, intensity will not affect the maximum speed of the electrons released. So each photon can give all its energy to one electron. Okay, so having more intensity means more photons, therefore more electrons potentially. But the increased intensity won't affect the maximum speed of the electrons, because each photon has a fixed amount of energy and it will give it all to an electron. Okay, and that's what you need to understand for the final point. So the student's wrong. So that's question 17, part A and B. Oh, that's the whole of question 17. Okay, so the photoelectric effect. Question 18 is about a laser pointer. So this is a diffraction grating question. So this is a core practical. I think this is core practical 6. Yeah, double check that. So it's one of the practicals that you need to know the method and what they want you to do in this experiment. So a teacher has a laser pointer. The laser pointer emits a narrow beam of plane polarized light. Describe how the teacher can demonstrate that the light from the laser pointer is plane polarized. Well, if it's plane polarized, it means it's only vibrating in one plane. So if you direct the laser light through a Polaroid filter or polarizing filter, yeah, you can buy these. The Polaroid filter is made of a crystal where it only allows the transverse wave, in this case light, to go through it if it's vibrating in the right plane. So if you rotate the filter by 90 degrees or until the light intensity decreases, should go to 0 if it's a plane, if the light from the laser is already plane polarized. Because if it's at right angles to the polarization of the laser light, then it will block it completely. Okay, that's the theory. So I hope that makes sense. These are the 2 points you need to make to get the 2 marks. So the teacher then shines the light from the laser pointer onto a diffraction grating. Yeah, so there's the diffraction grating. As shown, this produces a diffraction pattern with a central maximum in the center and the first order on each side. So they have only shown the one to the top of this diagram. Okay, so we have the theta, and in the next part of the question they've given you this distance and they've given you this distance for you to be able to determine the data you need to be able to use the equation. Okay, so what is the equation? You should know that if you are revising for your exam. The equation for the diffraction grating is n lambda equals d sine theta. Well, for the first order maxima, n is 1, so you don't have to worry about n. So there should be a second one as well if you can see it on the screen. If the angle's not too large, n2 will be near the top of the page. Okay, so that's the second bright fringe to each side of the central maximum. State the quantity represented by d in this equation. So d is the distance between slits in the grating. Adjacent means next to each other. Okay, so you need to work out d to put it in this equation, but normally the diffraction grating is labeled with how many lines there are, how many slits there are per millimeter. Normally that's what's written on the diffraction grating, so that's coming up to the next bit. They just want to know that you know what the D stands for. Okay, so that's the first part of question 18. The second part, the teachers made the following measurements. There's the values I've drawn on this diagram. Distance from the central maximum was 1.61. The distance to the screen was 2.74 meter. So that allows you to work out from using tan, which is 1.61, opposite over adjacent. So if I bring the diagram back, you'll see tan theta is opposite over adjacent, so you can work out the theta. Okay, so theta comes to 30.4 degrees. Yeah, you'll probably get a mark for that. I'm just looking at to see where they give the marks. Yeah, so you get the 1 mark for the use of tan, so you'll get 1 mark for there. Then we know n is 1. D, they've given you, they haven't given you d, so they want you to calculate the number of lines per millimeter. So you first need to calculate d, yes, and then from d you can work out the number of lines per millimeter. So if you change the subject of the equation round, they've given you the wavelength as 532 nanometers, which is 532 times 10 to the 9 meters. You put that in. Lambda over sine theta, the sine of the angle that you worked out using tan. So don't get confused. You don't use tan, you use sine in the equation. Tan is just used because of the right angle triangle on the measurements available when you do this experiment. So that's one of the things that you need to understand for this core practical. You use tan to work out the angle, then you use the angle using sine to be able to work out the position of the first order maxima. Okay, so n is 1, so it disappears. So you divide the wavelength by sine theta, it comes out to the distance between the slits in the diffraction grating of being 1.05 times 10 to the minus 6 meters. So you'll probably get a mark for calculating this. And then what you've got to do is to, obviously that means d, 1 over d is the number of lines per millimeter. So if the distance is there, it tells you how much you got per meter. You'd have this many per meter, but obviously it's not that of a meter size, so normally we give it per millimeter, and you probably round that up to 950 because obviously there will be some uncertainty in your measurements, so it'll be about 950 per millimeter if you calculated it properly. So I can see those are the 3 marks that we would get. Hope that makes sense. often in this question they actually give you the number of lines per millimeter, and they want you to work out the wavelength. Okay, so different forms of this question. If you practice past papers, you will find that they ask different things in different questions. Using this diffraction grating, part 3, and the laser pointer, only the first order of maxima and the central maxima are produced. Okay, so in other words, they couldn't see the second order maxima. Explain how the teacher, using the same laser pointer, could improve his value for this number of lines per millimeter. They basically mean how could you do it more accurately. So measure the distance from n equals 1, on each side of the central maxima, then divide by 2. This will reduce your uncertainty, okay? Because obviously you're finding it difficult maybe to get it exactly measured with your measuring instruments. Okay, so if you have a bigger distance, your real uncertainty divided by a larger one will reduce it, will halve your percentage uncertainty in working out one of the distances. And you could increase the distance from the grating to the screen distance. Sometimes they recommend a distance to the screen of about 4 meters. So depending on the brightness of the laser, yeah. So obviously it depends on the equipment you've got in your school and also the availability of space in the lab. Okay, but so if you do that, again, you reduce the percentage uncertainties. So these are the two ways of increasing the measurements. Increasing the measurements is a skill. So these kind of questions could also be asked of you in Unit 3, which is the skills questions. Both of the above would decrease the percentage uncertainty in measurements made to determine theta. So that will give you a more accurate final answer. Hope that makes sense. We're now on question 19, which is to determine the resistivity of this nichrome wire. Okay, so that's what it says in the first sentence. The circuit included an ammeter, a voltmeter, and a variable resistor. You get 1 mark for putting everything in the series part of the circuit, and 1 mark for putting the voltmeter correctly in parallel with a nichrome wire. So that's how you get the 2 marks. It then says the student varied the length of the wire in the circuit. For each length, she made measurements of the potential difference, and across the wire, she used the variable resistor to keep the current at 0.200 amps. So this is a controlled variable, okay? So that's something she kept constant. She obviously got the data and plotted it in a graph like this. Potential difference on the y-axis and length on the x-axis. So you can work out that the gradient is 4.15 divided by 1.00, the length. So the volts per meter is needed in the next part of the question. Okay, so the next part of the question asks you to determine the resistivity of the nichrome wire. Well, the equation that you're given with resistivity in it is that. Now we don't know the resistance, but we know the voltage and the current, and we want voltage in our equation instead of resistance because our graph has the voltage on it. So again, this is a core practical, and this will be either core practical, this will be core practical 7 or 8, I can't remember. One is 7 or 8, question mark. One of the core practicals, 7 and 8. One is resistivity and the other one is internal resistance. So you need to also know those 2 experiments in detail. So you also know from Ohm's law that R equals V over I. Yeah, so we can replace R with V over I. Now, whenever you got these core practicals, they like to give you a straight line graph like we just looked at. And in this case, they're giving you the cross-sectional area, which we need to know. So in other words, that's a constant. And I was a constant. So what did we do? We put V on the y-axis and we put length on the x-axis. These are our 2 variables. Okay? Change the length, measure the voltage. So if we rearrange the equation, we can see that V will be equal to rho, the resistivity that we want, I, which is a controlled variable, A, which is another controlled variable, doesn't change, times L. So if you see this is in y equals mx plus c form of the graph, which is, again, the core practical skill, if the v is on the y-axis and L is on the x-axis, that means the gradient that you calculated or can calculate will be equal to these three combined together. Okay, so that's basically what they want you to do. So they want you to get the m from the gradient. So once you realize that this is what they want you to do in the core practical skills, so you'll notice that core practicals are examined also in a theory paper. So once you have shown that you understand that this gradient will tell us what the resistivity how to calculate the resistivity, because I is fixed and A is fixed, and you get the gradient from the graph, they will give you 2 marks for how you show that on your graph. So you must show where you got your values from. I use the biggest triangle possible. For getting a large triangle, they will give you a 2nd mark. If you use a small triangle, you lose 1 of the marks. They tell you in the mark scheme what the minimum size of the triangle should be, but always use the maximum available as long as the figures make sense. Okay? So once you know the gradient is 4.15, m is 4.15, we know that m is equal to rho I over A, so therefore rho will equal m A over I. So you know the gradient is 4.15, we know the A is given to us, and we divided by the current, which was kept at 0.20. Okay? So you work out the resistivity is 1.10 times 10 to the minus 6. But don't forget, if you don't get the units, you won't get the mark, the final mark. So that's how you work out the resistivity. So again, this is very good practice to make sure you have done core practical 6. Finally, they want you to calculate the power dissipated from the nichrome wire to the surroundings when the length of the wire is 0.75 meters. So what you have to do, you have to go back to your graph, find 0.75, draw a line up to the line, to the plotted line, and do it across and see that at that length, 0.75, the voltage is 3.1 volts. Okay, use a ruler and a pencil. Okay, once you do that, we know the voltage from the graph. That gives you 1 mark. So show you're working on the graph. Then you can use power is voltage times current. Remember, the current was fixed. Multiply the voltage, and it's as easy as that. The power dissipated is 0.62 watts. And that is the end of question 19. Over the page, we go to question 20. Now, they started putting smart meters in the homes, and a lot of people don't like that. So they see it as an intrusion of privacy, but this is not what they're asking about. They want you to look at the intensity of the radiation coming off it. So a smart meter collects information about the use of electricity in each home, in the home. This information is transmitted to the electricity company, using radio waves. A typical smart meter emits radio waves with a power output of just 1 watt, so there's a P. An intensity of radiation greater than 4.5 watts per square meter is dangerous to people. So I is the intensity. The equation that is given to you on your equation sheet is intensity is power divided by the area. Now obviously, the further away you are from the source of the radiation that's emitted, the less intense the radiation will be. So don't go and stand right next to it. So it says an intensity of greater than 4.5 watts per square meter is dangerous to people. Okay? So a person stands 25 centimeters from the smart meter. Is that wise? Deduce whether the radiation emitted would be dangerous at this distance. So you need to work out from the inverse square law. Obviously, the closer you are, so this is the source, and you go out a distance r, then the intensity is over a sphere of 4 pi r squared. So that's why the area is 4 pi r squared, because it goes out 3-dimensionally. So if you then double your distance to 2r, the area will be 4 times as large. So that's why it's called the inverse square law. You double the distance, the area will be doubled, and therefore the intensity will be quarter. Okay, so you work it out. Don't forget that R has to be changed to meters from 25 centimeters, gives you an area at that distance of 0.79 meters squared. That's the surface area of the sphere at that distance. So you're standing there, so the intensity at 25 centimeters can then be calculated. The power is 1, the area is 0.79. It gives you an intensity of 1.27, which is less than the 4.5 safety limit. So it would not be dangerous at that distance based on the information we provided. Okay, so I think that some of this issue with the safety is also not just to do with the power, but the fact that it's pulses of radiation, so it could also have a resonating effect with your cells. So obviously you're not going to stand close to the meter anyway, but that's why people object to them, as well as the privacy. It is suggested that the energy per photon could be more important in determining if the radiation emitted is dangerous. The smart meter transmits frequency of 902 megahertz. That means the frequency is 902 times 10 to the 6 hertz. Calculate the energy per photon in electron volts. So again, you need to practice changing units from joules into electron volts. Remember, the conversion factor is the charge of an electron. Okay. Emitted by the smart meter. So first we need to show that we know how to work out the energy of this frequency, which is Planck's constant. This equation is given to you on the sheet. On the equation sheet, multiply this by the frequency and you get this many joules. Okay, but you want to calculate it in electron volts. To convert joules to electron volts, it actually uses this equation. So you divide the energy in joules by the charge, where the charge is the electron's value, which is on your data sheet, which is 1.6 times 10 to the minus 19. So you divide this value by 1.6 times 10 to the minus 19, and you get 3.74 times 10 to the minus 6. You can round that up to two significant figures, because you'll notice that we don't always have very accurate 2 or 3 significant figures in this case, because the data given here is 2 and 3 in terms of significant figures. So that's the first part of question 20. And that's part A and B of question 20. Now we want to go to the next page, part C. The display of the smart meter is shown. Okay, this shows a total electrical energy used in one day. Okay, so 6.85 kilowatt hours. A kilowatt hour is a unit of energy equivalent to 1 kilowatt. So if you leave 1 kilowatt of power running for 1 hour, you will work out how much that is in joules, because remember, power, energy, is equal to power times time. So basically it's a larger unit than a joule, because a joule would be 1 watt by 1 second. This time it's 1,000 watts for 3,600 seconds. So I've already worked that out here. So 1 kilowatt is 3.6 megajoules. Okay, so once you know what kilowatts are, this is basically GCSE level question as well. In some GCSE courses they'll do this. The kettle in the house uses a power of 1200 watts. The kettle takes 125 seconds to heat water to boiling point. Okay, it then switches itself off, automatic switch. A student suggests that boiling the kettle once uses less than 1% of the total energy shown on this display. So you've got to work it out. So the kettle, here's how much the kettle will use. Power times time again is 1,200 times 120, so it's 150,000 joules to boil a kettle of water. Then, if you then work out that this 3.6 megajoules is the 1 kilowatt hour, and it's saying that you use 6.85 kilowatt hours, so you multiply 6.85 by 3,600,000 joules, you get 2.47 times that. So you want to work out is what percentage of this is 150,000 divided by that, multiplied by 100 is 0.61, so it's less than 1%, so the student is correct. There's the end of question 20. Okay, in recent years they seem to have put more questions. It used to be that you only have 18 questions or so. They've now gone to 21 in this paper. So here there's a question on standing waves. A recorder is a musical instrument with a mouthpiece at one end, as shown. Okay, so you blow in there and it sets up a standing wave as shown here. Okay, that's what musical instruments do. String instruments have standing waves set up on strings, tight strings, and in musical instruments, wind instruments, it sets up a vibration of the air column inside the tube. Okay, when the musician blows into the mouthpiece, a stationary wave is produced in the air column. Inside the recorder, a stationary wave has antinodes at both ends. Okay, 2 antinodes at both ends is a trough and a peak, if you like. So that's not a complete wave because you need to go back to the next peak in each part of the wave to get a full wavelength. So the stationary wave has antinodes at both ends as shown. Calculate the frequency of the sound produced by the stationary waves. Now this is an application of Core Practical 5, I think, where you do standing waves in the lab. Usually in a lab you either use a vibrating wire or a vibrating string, and you set up antinodes and then you work out the formula. So the formulas are given on your formula sheet. Okay, so the speed of the sound, calculate the frequency of the sound produced by the stationary wave. So first they give you the speed of the sound. They want you to use the wave equation, but they want you to realize that the wavelength is twice the length of this, yeah, because this is only half a wavelength. They're setting up antinodes at both ends. So you have to realize that lambda over 2 is 23.6 centimeters, or in meters 0.236. Once you do that, you can then use the wave equation where lambda is 2L, yeah? So you divide it by 330 meters the speed by 2 times the length of the vibrating air column, and you get the fundamental frequency around 699, where you could write that as 700. Okay, that's the first part. The second part of the question is that the recorder comes from 3 separate sections. Okay, they slide together as shown. The musician plays the recorder and produces the same frequency as in part 1, but the temperature of the air is increased. Okay, as the temperature of the air increases, it means the speed of sound also increases. So as temperature increases of air, the speed of sound also increases. Okay, they're telling you that. You don't need to know, you don't have to worry about that. Explain how the musician can adjust the recorder to produce the same frequency at a higher temperature. Well, if the velocity's gone up due to the temperature increasing, to keep the frequency the same as in 1, the wavelength would need to increase to compensate. Yeah? The wavelength would need to increase because V equals F lambda. Alright, so for this to occur, since lambda equals 2L, the length of the vibrating column of air needs to increase. Okay? And this can be achieved by loosening the sections to make them longer, by sliding the sections further apart. So that's how you could do it. So if you make the length longer, the wavelength becomes longer, so that would keep the frequency from changing. So V goes up, we increase the wavelength, so the frequency can stay the same. Okay? Finally, the last page of the exam is on a violin. A stationary wave is created when a string is plucked. A violin string has a fixed length. Okay? So L is fixed, but the tension can be adjusted. Yeah, so those are the controls at the end of a violin string or a guitar string where you can change the tension. When a string is plucked, it produces a sound with a frequency of 432 Hz. The string is then adjusted to produce a sound of frequency 440 Hz. Calculate the percentage increase in the tension of the string. Well, since we know that V equals F lambda and the vibrations of a tense string depends on the string, that's the kind of the density or the mass per unit length of the string that's being used. So the velocity, which is proportional to the frequency, is proportional to the square root of tension. So you can replace V with F lambda. Lambda, since the length is fixed, the lambda doesn't change, so that's a constant, and that's a constant. So the variables are F and T. So F is proportional to the square root of T, or you could square it out and say F squared is proportional to T. That means if you increase the frequency from 430 to 440, you have to square the second frequency divided by the first frequency. Now this is the math. So the ratio of the frequency squared should be equal to the ratios of two tensions. So if you do that, it shows that 440 squared over 432 squared gives you an answer of 1.037. Okay, if it was the same frequency, it would be 1.00, so it's gone up by 3.7%. So tension 2 must be 3.7% more, yeah, than tension 1. So that means a 3.7% increase in tension. Well, I hope that helps you understand the level of analysis that you need to make to be able to get the full level of answers for the A-level paper, the Unit 2, which is normally in May, late May I would imagine. I haven't looked up the dates. So we will do more of these practice papers as we get closer to the exams for people who are either retaking it or taking it for the first time. So if you found this video useful, please like it, share it with your friends so we get more people getting help on how to communicate their answers. And if you want to know when the next exam paper is ready that you can go through, then please subscribe and you'll be notified if you hit that bell notification symbol on YouTube. So thank you very much for watching, and I'll see you in the next video, hopefully. Bye for now.